Here's today's poser. A 3-kilogram ball falls from a height of 12 meters. What's its speed at height? 6 meters. And the potential answers are 2.6 meters per second, 6.5 meters per second, 11 meters per second, or D, it can't be determined. The answer is 11 meters per second. How do we get this? Well, we could use our kinematics equations, or the simplest way to solve it is to say that the ball has fallen 6 meters and use our loss of gravitational potential energy to calculate the kinetic energy, which then can be used to solve for velocity. And if you're not sure how to do that, I'd encourage you to review that from our previous lecture. Okay. Hello everyone, I'm Mr. McBrien. This is SPH3U, Conservation of Mechanical Energy, or the Forever Ball Part 2. The Ontario curriculum states that we need to use the law of conservation of energy to solve problems involving work, gravitational potential energy, and kinetic energy, and that we should be able to describe energy transfers and transformation. This is what we're going to focus on today. So we're going to talk about the law of conservation of energy, and we're going to apply that to kinematics problems we previously solved using our kinematics equations. Okay, so from last week, we have conservation of mechanical energy. What we're saying is that if you don't do any work on an object by an outside force, then the total mechanical energy of the system is going to remain constant. We can refer to that as delta E equals 0, or the sum of the gravitational potential energy plus the kinetic energy at any time is equal to the sum at any other time. And we talked about our forever ball back last week. Let's talk about it again. If we have perfectly elastic collisions and no friction, then energy is going to be perfectly transformed between kinetic and gravitational potential energy. And once we have this extra special ultra super forever ball, given the height of the ball at any time, we can solve for kinetic energy and gravitational energy. And given the kinetic energy and gravitational energy, we can solve for speed. So last week we solved at two extremes. We started with the height being 12 meters when we drop the ball. And of course when we drop it, the velocity equals 0. And we calculated our gravitational potential energy to be 3.5 times 10 to the 2 joules. And we considered state 2 just before the ball hits the ground, when the height equals 0, and the velocity then can be determined because the gravitational potential energy is 0, and thus the kinetic energy must be 3.5 times 10 to the 2 joules. In other words, all of the energy has been transformed from gravitational potential energy to kinetic energy, and we solve for the velocity, getting 15.3 meters per second, or we rounded for sig figs to 15. Okay, and we used, of course, our expression. So now the big question becomes, does the ball have to be at the top or the bottom to solve this problem? And no great surprise, we allow the ball to bounce, and we say to ourselves, does the law of conservation of energy still apply? Because if the law of conservation of energy applies, then we can solve for the other, for this, because the energy remains constant. So we take our case of it bouncing to a height of 4 meters. We know the gravitational potential energy, and we still know the total energy because it was constant, and so we can solve again for the kinetic energy. And all this really implies is that it doesn't matter how many different states we have, we can solve for all of them, provided we have enough definition. And so what we're going to do is fill in this table, but before we do, maybe we can talk about a general recipe for this approach. So let's talk about that. If we want to solve for a given problem using the law of conservation of energy, it's not a particularly difficult thing to do. First off, we need to declare our states so that we're clear on which parameters belong in which time frame. And for convenience, you can just say state 1, 2, 3, etc. Then the easiest approach to take is to identify the state that's best defined. If at all possible, we're going to calculate the total energy for the system using a single well-defined state. And then once we've done that, we can solve for any missing terms by keeping the total energy constant. Again, our expression of E total being constant, and knowing that we only have two terms for our mechanical systems. So, some nasty physics teachers may give us some situations where we can't define the number of joules exactly. This is typically when you don't know the mass of the ball or the other object that we're considering. If this happens, it's not a big deal. You can either use algebra to cancel out the mass, or you can insert a probe value for the mass, which you can be confident will cancel anyway. Okay, so in class we're going to work through an example. I'd encourage you to do the same with this problem. So it's not unlike the one we had at the beginning. We have a 3 kilogram ball dropping from a height of 12 meters, and it bounces to a height of 4 meters. And the question is, what's its speed? So we have our initial state at a height of 12 meters and a speed of 0. This can give us our energy total. And we have state 2, where the ball has a height of 4 meters. And we can solve for the missing kinetic energy term using that, and then use the kinetic energy term to get the speed. I'd encourage you to pause the movie and take the time to do that calculation. Now in class, what we're going to do is in fact fill out this entire table. So this is kind of a classic physics question that we can expect to see on tests on a regular basis. Hint, hint. So for this kind of a table, we can just work our way through and in this case use all of the heights involved to calculate the velocities. And if you do it right, and you calculate the kinetic energy and the gravitational potential energy, they should all total to 350 joules when accounting for rounding errors. So I'd encourage you to take the time to work your way through those problems and do those 5 problems before you continue. Okay, now you've done a bunch of exercises and you've got your feet wet with conservation of energy problems. Can you think of any other systems that we can treat this way? So stop and think for a second about any other systems like that. They're going to involve gravity and speed, and I'll list some that I thought of off the top of my head. So the kind of closed systems that we can treat with the law of conservation of energy could be roller coasters, pendulums, swing sets, and ramps. Essentially any system that doesn't have an outside force acting on it. Okay, one final thought before we do some work on this. Can we find the velocities involved? We've talked about speed over and over again. Can we fill in the velocities for this table? Please pause the movie and think about this for a second, and then come back and we'll discuss it. Okay, welcome back. So hopefully you've noted the fact that these heights, we don't have any time associated with these heights. And based on that, we have no idea of the direction that the ball is going. And in fact, it's irrelevant to our question. The direction is undefined because the time frame is undefined. And of course, this is consistent with our original point that energy is a scalar quantity rather than a vector quantity. So we have a speed that we can define here. We do not have a velocity. Okay, so now the exercise for us to perform. This should be very straightforward to you based on what we've done so far. What we want to do is fill in this table, filling out the kinetic energy for our roller coaster and the speeds and heights for the given positions. So you should be able to figure out which we're asking for here. We're looking for kinetic energy and gravitational potential energy in the left-hand side of the table, and speed and height in the right-hand side of each one of the columns. Please go ahead and fill those in, and when you're finished, you should be an expert in conservation of energy problems. Now, I'm going to give you the weight of the roller coaster, but keep in mind that you could be asked to solve for the velocity, for the speed of the roller coaster, without actually having that mass. And you should certainly make sure that you know how to solve for that speed in that way. Okay, so further practice, please complete that roller coaster seat work question, and I'd like you to stop and take state number 4 and solve it a second time without the train's mass for practice to make sure that you can do it, canceling the mass. And please look backwards and make sure that you did complete the problems from last week's homework. Thanks very much, and have a great night.